Welcome to another video for General Science. In this video, we're going to discuss energy and its forms, and I'm going to use some superheroes to illustrate and explain these concepts. So let's go ahead and dive in. So to understand energy, let's revisit work. Okay, you'll remember work from our previous chapter, and again, we're discussing work in a physics sense. So work is just another term for energy. They happen to have the same units, which if you remember are joules. Okay, so you measure energy in joules and you measure work in joules. So it's interchangeable in this case. So then the last chapter we said that work equals force times distance. That's a horizontal force, right? So if I'm pushing something, as long as there's a distance I'm creating a difference in distance, then I'm creating work, right? Now, of course, there are different angles in which you can apply work, and that's when you start to use trigonometry, cosine, theta. But in this case, we just discuss the direction of the change of forces in the exact same direction as the force applied. Okay? So in this case, for this chapter, we're going to discuss vertical force. Okay, so that's going to change a little bit because now we're talking about up and down, and mainly falling objects, so a falling mass. So that changes our equation just a little bit. Take a look at force. Now force is mass times gravity, right? The mass of the object times the gravitational force. And then our distance is no longer a horizontal distance, but a vertical distance. So now we're talking about a difference in height. So our new equation is work equals mass times gravity times height, which is also the equation for potential energy, okay? PE. All right, so let's take a look at this. Consider this for a second. Okay, you might remember this from a recent movie in Spider-Man, but that was inspired from a piece in a comic book, an original comic book. And off the top of my head, I don't remember which series of Spider-Man comic books this is, but this is a legendary story where Gwen dies, where Spider-Man actually accidentally kills Gwen. And in order to understand why and how Spider-Man accidentally kills her, we're going to need to understand the physics behind what's happening here, or potential energy. So again, we're considering Gwen's mass, m, the Earth's gravitational pull, which as she falls, the gravity is pulling her down, so that's creating the force that's pushing her down. And then we also consider the height. And you notice here that she's on the edge of a bridge here, and that's a really tall height. So we consider the height in this case. So we consider her mass, the gravitational pull, and the height that she's falling from, or that she got pushed from by the Green Goblin. Now, we want to, there's a direction, or I'm sorry, there's a connection between the height of an object and the velocity that it goes. And this equation is velocity squared equals 2 times gravitational pull times height. Okay? So we're going to do a little bit of algebra here to derive a new equation from this, because you have to understand now. So potential energy works great when you're standing up, like Gwen was standing up on the bridge, for example. But what about the math for when she falls? So there is a correlation, there is a connection between how high she is and how fast she's falling. And this is the equation that we use to derive our new equation that we're going to use. So first of all, what we're going to do is we're going to consider the mass of Gwen. So notice what happens to my 2GH. Now we add mass in there. Now whatever you do to one side of the equation, you must do to the other, right? So we have mass. So we've considered the mass of Gwen, okay, with the other factors, gravity and height, and then velocity squared. Now we want to get rid of that 2 on the right side of the equation, so we're going to multiply it by its reciprocal. And again, whatever you do to one side, you must do to the other. So we end up with this new equation, right? So half mass velocity squared equals mass GH. Now it just so happens that half mass velocity squared happens to be the equation for kinetic energy. Kinetic energy meaning energy that's in motion, as opposed to potential energy, which is stored up energy that is not in motion yet. Okay, so potential energy being when on the bridge, and kinetic energy is the energy that is being made as she falls down. So these two equal each other. And now we're diving into the concept of conservation of energy, which we'll explain here in a second. So as the kinetic energy, or actually as the potential energy is at its highest point, okay, the kinetic energy is at its lowest point, because if you consider the equation, okay, if you consider the equations that each of these represents, okay, if Gwen represents the circle and our bridge represents the blue rectangle there, consider the fact that Gwen at the beginning of this situation is at the very highest point of the bridge. So H is at its highest point. That quantity is at its highest point, which means potential energy is at its highest point. And since she's not fallen, velocity is at its lowest point, which is 0, which means kinetic energy is at its lowest point. So it's an inverse relationship. Okay, now notice what happens when Gwen begins to fall. My H is no longer at its highest point. Now you can say she's maybe halfway through or halfway down, so that means that H is now half of what it used to be, so it means that quantity is now lower. But on the left side of the equation, you notice velocity squared. Now her velocity is actually gaining more and more of a quantity because of the gravitational pull. Remember, gravitational pull is meters per second squared. So she's not, her velocity, she's falling at an increasing rate. She's accelerating towards the ground. So her speed is gaining more and more quantity, or more of what's the term? It escapes me. But she's going down faster each second. So that means kinetic energy is increasing. So at the same time potential energy is going down, kinetic energy is going up in the same, in an equal amount of force. Okay? So as kinetic energy goes up, because velocity is going up, right? Because she's falling faster and faster, our potential energy is going down because the height is going down. Now, just the instant before she hits the ground, kinetic energy is at its highest point because she's going at the fastest point that she's going to go in this particular situation. Her velocity is at its highest point the instant she hits the ground, right? So kinetic energy is at its highest, and potential energy is at its lowest point because now its H is basically 0. From the point that she fell off, she was pushed off the bridge by the Green Goblin, her height had been decreasing more and more and more up until the point where it almost reaches 0. So it's at its lowest point, okay, until she hits the ground, and at that point the height is 0 and velocity is 0, which means everything is 0. It equals out still. Okay, now in this particular story she actually doesn't hit the ground. Something else happens. So think of this as a seesaw. Okay, here I have my potential energy and kinetic energy. So at the highest point, my height is at its highest point with potential energy, and my kinetic energy is at its lowest because there's no velocity. I haven't fallen yet. And then as Gwen falls, as the object falls, height goes down, which means potential energy goes down, and velocity goes up because they're accelerating towards the ground, so kinetic energy goes up. Okay, so it's a seesaw, and it goes, and it's inverse to each other. Okay, because you got to remember, originally these two equal each other. So Gwen is at a very high velocity going down. Okay, it's a very tall bridge. That means the velocity that she's gaining as she falls is pretty immense. Now the problem is that Spider-Man doesn't understand these physics. Because what he decides to do is that he decides to shoot his web, he catches her, but instead of allowing her to have a gradual descent or gradual fall, he quickly catches her, and he catches her before she hits the water. But unfortunately, her rate of speed, her rate of stopping was so drastic that all that energy that she had gained from falling down was essentially her neck essentially absorbed all that energy, and he broke her neck by accident. Okay, so it would have been the same as if she would have hit the ground. So you got to consider there's a lot of velocity that's being gained, a lot of energy that's being gained as an object falls, and when that object hits the ground, that velocity goes to an instant 0. Instead of it being a nice little gradual descent or slowing down, it's an instant stop, and that force has to go somewhere. All that energy has to go somewhere. And usually the object absorbs that energy. That's why things splatter, because all that energy is now dispersed throughout the object. And if the object's not strong enough to absorb that force, it'll break, splatter, or what have you. And in this case, Gwen, her neck is what absorbed all that energy, and Spider-Man accidentally killed her. Now, of course, Goblin pushed her off, but Spider-Man's lack of understanding of physics, unfortunately, did not pay off for him. All right, well, let's go back. Let's go to my original character here, Flash, that you see in the very beginning. So what does Flash have to do with kinetic energy? Well, as you know, Flash is very fast, right? So his velocity is enormous. So we're going to use kinetic energy, half mass times velocity squared. Okay, this is an equation that you do have to memorize along with potential energy. So how much energy does the Flash need to go fast? Now, I could have done a very traditional lecture with this particular subject, but I wanted to have a little bit of fun with it and use some comic book characters that I know you guys watch, listen to, or what have you. So let's use some of these theoretical concepts of superheroes and see how it stands up to actual physics. We already saw the error that Spider-Man did. Now let's take a look at Flash. Is Flash actually physically impossible? Let's pretend Flash weighs 155 pounds, which means he's 70 kilograms, right? Our standard unit of measure for science. So mass is 70 kilograms. Let's also pretend that in this case, Flash is traveling 1% the speed of light. And in that case, that would be 3 million meters per second. That's really fast. Only 1% of the speed of light. And of course, he can, I have to go back and check, but I think he can almost travel the speed of light. You guys will have to check up on that. Correct me on that one if I'm wrong. But either way, let's just assume just 1% of the speed of light, which is still pretty fast. So let's say he's traveling that fast. How much energy is he actually using up by traveling just 1% of the speed of light? Well, we replace our m with our 70 kilograms, our velocity with 3 million, and we square that term, and we end up with 315 trillion joules. Okay? Now that actually translates into 75 trillion calories. Now, this is not the same kind of calorie that you consume in your food. Okay, this is actual physics calorie. So let's translate that into actual calories that we have a better understanding of in our diets and food and such. So 1,000 physics calorie equals 1 food calorie. So in other words, we have to divide our 75 trillion physics calories into 1,000 to get an actual food calorie, which comes out to be 75 billion calories. So think about that for a second. So Flash, as he's going the speed of 1% the speed of light, consumes 75 billion calories. That means he needs to eat 75 billion calories in order to go that fast. Just like you, when you go exercise and you go to PE class, the kinetic energy that you end up using up in your class, that energy comes from somewhere, and that usually comes from the calories that you have consumed for breakfast, lunch, or even the dinner before, okay? Or fat storages that you have in your body. So, how does that translate? 75 billion calories, that's pretty difficult to imagine. Well, I'm not sure this is going to help me much, but that basically adds up to about 150 million burgers. So the Flash has to eat 150 million burgers to travel 1% the speed of light. And again, we're assuming that friction is not an issue, so none of the energy is being wasted in friction, okay? Because that would be a whole nother problem in and of itself, the force of friction. Because as fast as he's going, let's say he was going 500 miles per hour, how much energy would that require for him to stop? Okay, now we're talking about 80,000 pounds of energy that he would need, and I know pounds is not necessarily an energy unit, but 85 pounds per foot to stop. So he has to have also very strong bones and skeletal tissue and ligaments and tendons and all that to stay together by causing all of that velocity that he's created to all of a sudden come to a zero, to a stop. Okay, so the Flash has some issues with physics, or physics has issues with the Flash. But again, this is fiction, so it's okay, not a big deal. But still, it's still fun to consider and to apply into physics. So can you imagine 150 million burgers in order for him to sustain the amount of work that he does? That's enormous. That means he has to eat as fast as he can run. And again, he's also wasting energy by eating also. So in any case, that does it for this particular presentation, energy and its forms. You do have to memorize the equations that I showed you in this video, and there's more to come. So thanks for watching and listening, and good luck in your studying.